This video looks at what information a null vector contains and then goes on to show how a null tetrad in the Newman Penrose Formalism can be constructed. And two examples of this process are shown using Minkowski and Schwarzschild spacetimes. Right, so let's consider a light ray moving in the positive direction of the x-axis. And this is shown on the Minkowski space diagram over here. Vertical axis time, horizontal axis x, and we have a light ray moving in the positive x direction, and we could represent that on this diagram as this vector here. And the components of this would be this object here in the time and x directions, and the magnitude of this vector would be given, magnitude squared would be given by this object here, which gives us the line interval, the space-time interval here for this light ray traveling along the x-axis. And in a time delta t, the light ray has traveled a distance delta x, so we have delta x is c delta t, and so the magnitude of the velocity we saw on the previous slide becomes this object here, which is 0. So what we have is the distance traveled by light on the space-time diagram is 0. Now vectors can be written in this format here. In the Minkowski spacetime, we're in a flat spacetime, and the basis vectors I, j, k and the time direction are of unit magnitude, so they form an orthonormal basis and they're mutually orthogonal, of course. And a light vector has a magnitude square of equal to 0. So that vector is light-like, and we find that its magnitude, this operation here, is the Minkowski metric, and we find that it's 0. The magnitude squared is 0, also the magnitude is 0. The distance traveled by light is 0 in Minkowski space. So a light-like vector is a null vector that carries useful information about the local structure of space-time. And so just also while we're here, the time-like vectors, we find that this magnitude squared is less than 0, given the metric I'm using, which is a -1, +1, +1, +1 signature. And for space-like vectors, we have mod v squared is greater than 0. Now, we can build a null tetrad from an orthonormal tetrad. So imagine a congruence of time-like geodesics, these red lines here, a congruence in that through each point P, there is one and only one geodesic passing through it. That covers space-time with time-like vectors being tangent. So time-like vector v here, little v here, is tangent to the geodesics, and the geodesics are the world lines of some observers. Now, three vectors belonging to a tetrad are shown below on the right here. So here we have the time-like vector here, tangent to the world line of the observer, and this observer is carrying along with them at all points along this world line these three spatial axes, of which two are shown here, E1 and E2, and each observer carries that along with them. So that is an orthonormal tetrad. Right, so our orthonormal tetrad has these vectors here, v, I, j, k, and the time-like and space-like parts are seen to be, the time-like part gives us this, for the metric that I'm using in this video, and the space-like parts give us these. Now with orthogonality, we have all these mutually perpendicular, so scalar products are 0, and our null tetrad then takes the form, and just note here the I in this will be a complex I, so L will take this object here, time-like plus a space-like, N will be the time-like minus a space-like vector, and M will be this object here with the complex number I, and the conjugate will be this one here, minus I. Right, we can check this claim. So we've labeled L, N, M, and M bar, and we can just check by taking the various scalar products. So L dot L gives us 0, telling us this is a null vector. L dot N, well, this is one of the normalizing conditions, but it will be equal to -1, following through the steps here, given the information earlier. N dot N will be null as we go here. L dot M will be orthogonal, and hence the 0 here. N dot M, orthogonal as well. M dot M bar is a normalizing condition. We'll see that is 1 here if we carry through these operations. L dot M bar is orthogonal, n dot m bar is orthogonal. And to summarize, our three conditions are the null conditions. The vectors dotted with themselves, the scalar products of the vectors with themselves are 0 because they are all null vectors. We're going to form a null tetrad. They're orthogonal, L dot m, N dot m, and so on are orthogonal. And then we have the normalizing condition, these two extra ones here. L dot n is -1 for the metric I'm using here, and m dot m bar is +1. Now, we've seen in a previous video on tetrads, we found an orthonormal tetrad basis to be the set of vectors, these ones, and we can build our null tetrad by setting E0, E1, E2, E3 equal to L, N, M, and M bar, and the components of these will be E0 alpha will be L alpha, all this object here. E1 alpha will be this, so the components of E0, E1, E2, E3 are these objects here, and E2, E3. All right, so they're the components of our null tetrad vectors. All right, now these vectors lead to a frame metric if we take the scalar product of these, which is these objects here. And when we do that, given the normalizing, orthogonality, and null conditions from earlier, we end up with this frame metric here. All the others drop out except for L dot N, N dot L, and over here, M bar dot M and M dot M bar. All the others are 0. Now notice that the frame metric is its own inverse, because if you multiply it with itself, you get the identity matrix. And so gamma mn, lowered, both indices lower, is this, and gamma mn with both indices raised are this. It's its own inverse. Also, just notice a relationship between our tetrad basis vectors here and the frame metric, what it does to them. E0 becomes, when we raise the index to the upper place, is equal to minus E1. E1, when we try to raise the 1 index, we end up with a negative E0. When we try to raise 2, we end up with E3. Here, when we try to raise this 3 here, we end up with E2. That's the effect of this frame metric. Next bit. Now, the relationship between the frame metric and the coordinate metric at some point P was found in the previous video on tetrads to be this object here, G alpha, just using some notation in modern textbooks. Go to this object here, the gamma m, where each of the axes, unit vectors in the direction of each of the axes carried by the observer. So here's a time-like axis here, and these are the two space-like ones here. There's a third one, which I can't show on the diagram for obvious reasons, so it's suppressed. And we can build from this component here and the individual little vectors that make our frame, our tetrad, we can build the metric in the coordinate basis. And that is G alpha dot G beta is this object dotted with itself, which gives us this. So we have our frame metric, and then we have these components here, which we've seen to be the components of our tetrad vectors, our null tetrad vectors. So the vector axes of this tetrad are given by gamma m is this object here, is that. That's in index in the lower place. And we see that the line element, ds squared, is this object here, which we can then write out as gamma mn, this object, times this object here. And that helps to tell us, also we have from that same video too, em upper was em lower alpha d alpha. So this is in the cotangent basis here. This one here is in the coordinate basis. This is in the tangent basis. This is in the tangent basis. This is in the cotangent basis, or the dual basis. This one form here. And we found the tetrad basis vectors and the tangent basis to be given by this object here. This is a tangent basis, right? And when they're raised, they're in the cotangent basis, which I'll leave that for now. Right, in the same way as in the previous slide, we had this. Remember, this was its own inverse as well. So we have this, and again, just to remind ourselves, here are the components in the upper index place here. So that now gives us meaning to what each of these are. And so what I'm claiming is that this object here is the inverse metric, and we're going to see how this here comes about. So I'll give an explanation next and how it is that we get this. So here's our metric, the inverse metric, and it's made up with these components multiplied together. So how did we get that? All right, let's see how this came about. We know that this relationship is given by this, and we know that here's our frame metric, and it is its own inverse. And just to remind ourselves again, here's each of the components, right, with the upper indices, the contravariant components. All right, so let's expand this out and see what we get. Well, when we do that, expanding that out, gamma 0, 1 is starting here, row 0, column 1. We have a -1, and so m here will be 0, n will be 1. Alpha, beta, and when we do that, if we go down here, E0 alpha, and then E1 beta, if this were a beta here, that would be N beta, and so that goes in here. Likewise, flipping those, this one here, gamma 1, 0, row 1, column 0 is this object here, and expanding that out, and that will give us minus N alpha L beta. Same over here, row 2, column 3 gives us a +1. And then alpha beta 2, 3, 2, and 3. And then over here, gamma 3, 2, this one, row 3, column 2, that one there. And that's +1, so that gives us +1 here. And 3 alpha gives us the M alpha bar. And E2 will give us the M beta, E2 beta, if that were beta, that'd be M beta, and so on. And we see how this comes about. We also have, through the same reasoning, this object here, again through the same reasoning. Now, as an example, let's consider the Minkowski line element in spherical polar coordinates. Here it is, this object here. And in the co-basis or cotangent, the basis vectors are these objects here, c dt, dr, r d theta, r sine d phi. These are our cotangent vectors or dual basis vectors, and we can form a null tetrad in this format here using the dual basis, these objects here. Okay, and what that tells us now is that the components now, right, L lower alpha, L covariant alpha in the lowered index position is this object here, same N alpha, this object here, M alpha is this one, and so on. All right. Now, from the new expression we have for the metric, G alpha beta is this object here, we can do G00 and substituting in. Okay, and then we substitute in from up here. So L0 is 1 on root 2, N0 is 1 on root 2, minus in front, next minus here. N0 is 1 on root 2, and L0 is 1 on root 2, and M0 is 0, M bar 0 is 0, right there, so they disappear. And when we calculate this out, we get minus a half, give us -1. G11 in the same way, if we calculate through here, we'll notice that M1 and M1 bar, so M1 there, 0, M1 bar is also 0, so they drop off. And again, we're just left with these objects here, and they give us as well +1. All right. Next bit, G22. When we substitute in, same thing here, L2 and N2 are going to be 0, they're going to disappear, and now the M2 and M2 bar terms kick in. We have R over root 2, so that'll give us R squared on 2, plus R squared on 2 will give us R squared, and we know the metric has R squared in it. G33, substituting in again, same thing. Notice L3, N3 are 0, M3 and M3 bar are not, they're these objects here. And when we calculate through with that, I times I is -1, multiplied by another negative gives us +1, and we're ending up with r squared sine squared theta all together, just as we have in the metric. So this method here does deliver this metric. Just confirming that. The inverse metric, of course, is this. And what we can do now is we can get the upper index through using the inverse matrix to raise the lower index here. And when we do that, we can start with this object here, the components here, and we can raise those. So LT is GTT times LT, which is L lower t, sorry, which is 1 over root 2. So GTT is minus 1, there it is up there. Minus 1 times that gives us negative 1 on root 2. L R contravariant, or raised index r, is GRR times 1 on root 2. So because L lower r is here, 1 on root 2, and we can raise that. So we have 1, GRR is 1, and 1 on root 2 here, 1 on root 2, there it is, 1 on root 2, because it's 1 on root 2. So the indices in the upper position, L with alpha raised, becomes 1 on root 2 minus 1, 1, 0, 0. And we see that L dot L is L lower alpha, that, dotted with that, and we see that that gives us 0. So we see that L, again, that works. L is our null vector, so L dot L should be 0. Same reasoning, we can raise the index alpha here on from the lower position on n to the upper. In the same way, when we do that, we get this object here, checking n dot n gives us 0, so it's a null vector. L dot n should give us minus 1, as we saw earlier from the normalizing condition. So when we do that, working through this, we get minus 1. And also from M alpha is this object here, we can raise that, again using the metric to raise it. G theta theta in the upper position comes from the inverse metric, so it's 1 on r squared times this object, gives us 1 on root 2r. Same thing, raising phi index here, same way, and we get this object here. And that tells us that M alpha in the contravariant position, upper index, is this object here. Checking M dot M should be this by that. When we do that, we get 0. Again, it's a null vector as it should be, so that's working out. For the complex conjugate, we have this object here, M dot M bar, gives us, working through that, we get 1 here, which is what we wanted as the normalizing condition. All right, next bit. We should have, right, the Schwarzschild line element in advanced Eddington-Finkelstein coordinates, u, r, theta, and phi. We're going to do another example. So let's take the Schwarzschild line element, but now in the advanced Eddington-Finkelstein coordinates, and using the metric that I'm using, we have this object here, this one, which is a previous video on this channel on the Eddington-Finkelstein coordinates. You'll see it there. How we arrived at this object, you'll find in that video there. All right, so the line element is written as ds squared is g alpha beta dx alpha dx beta. And we find that if we just expand it out, guu du squared plus gur du dr plus, notice these cross terms here, they're symmetric, and we get this object here, because remember on the previous page we had a 2 in front of the du dr. We need to split that out so that we have, because there's a cross term there, here and here, and when you add them together you get the 2. And we get g theta theta d theta squared, g phi phi d phi squared. Okay, so the metric is this. I'm just going to replace the rather large term at the front there with the symbol f, letter f, and we'll just put that in here now. Okay, and we notice that if we just swap this minus f and put it down here as plus f, and take 1 over r squared and 1 over r squared sine squared theta, but keep the 1's here, when we multiply this and this together, we get the identity matrix. So we know that the inverse of this is this object here. So the inverse metric then is given by this object here. Now you can do that with row reduction operations and so on like that, or just an educated guess, and you'll find that when you multiply them together it works. So there's your inverse metric right here. Now, in general, L alpha and N alpha are aligned with the outgoing and ingoing tangent vector field of the null radial geodesics. So when we go looking for our null tetrad, we just start with the premise. We begin with the understanding that these are pointing in the radial null geodesic directions. Now, if that's going to be in the radial null geodesic direction, why not start with L, as LR dr is simply dr, unit vector in the radial direction. So L alpha will be this object here, 0, 1, 0, 0. And if we wanted to find the index lowered, then we use the metric to lower it. And we see that when we check through the metric to lower it, if we wanted to lower the R there, then we need an R here. And the only other thing that's non-zero in the metric was where alpha was equal to U. So this then must be L lower U. So LU equals G UR LR. And when we look, we see that when we multiply, if LR is 1, that's 1. And this term here in the metric on the previous slide was 1, so that just gives us 1. So in the lower position, L lower alpha, is this object here. LU is 1 and all the others are 0. And if you have a look at that, this one, the scalar product of, so the scalar product L with itself, L dot L, will be this dotted with this, and you'll see that that is 0. So already we have a null vector. All right, next one. For the angular part, well, it's the same as the Minkowski metric. So we just use those null vectors, this one and this one. So that's convenient that way. Now, what we need to do is find out what n is. We've got L, we've got the m's, both m's. We just need to know what the n vector is. And then, so what we do is we go to the metric in this form here, and we're going to plug in some information and solve for the components n beta. So we solve for the individual components. Well, let's start with UU, and we know that that was minus f. And when we substitute U into here, we get this object here, minus 2LU NU. LU, as we saw on the previous slide, was 1. So it's minus 2NU is equal to minus F. So that tells us that NU must be F on 2. Remember, F was that big expression, which I'm not going to use here. So we'll just continue to use the letter F. So F on 2 will give us the first component NU. Next, the next non-zero component, GUR, which we know to be 1 in the metric. So substitute in the L, so we have minus LU NR minus NU LR plus these objects here. Now, these all drop out to 0, so MU, MR, they're all 0, so we don't have to worry about those. And we know here that LU is 1 times NR minus NU times LR. Well, LR lowered was 0. So that disappears. So all we're left with is this first term here, and we know that LU is 1. So that's just minus NR, which is equal to 1. So NR is negative 1. So that in turn gives us N with the lowered index alpha is these components here, which is just this object here. Now, raising individual indices, U in the upper position, we use the inverse metric to do that. If we expand that out, UU times NU plus GUR NR, well, we know that GUU raised was 0. NU was F on 2, so that's going to disappear the first part there. GUR was 1, and NR was negative 1, as we've just found up here, so that equals minus 1. NR, GR beta, and then substitute in turn U and R, U and R, and we find that GRU is 1, NU is F on 2, GRR is F, NR is minus 1, and when we work that through, that's equal to minus F on 2. All right, so that leads to N with the alpha in the raised position, raised index, these components here, that's object here. And if you also from earlier, M alpha was this, M bar alpha with these in the raised position with these two objects here. So in summary, what we found is L with alpha in the upper index is this, L alpha in the lower position, alpha in the lower index position is this object here. And you can see that that dotted with that, L dotted with itself, L alpha up times L alpha down, that'll give us 0. Same here. Notice these. If we do the scalar product here, we're going to have n with itself. We're going to see that these will cancel out. -1 times f on 2 plus f on 2 times 1. They'll go to 0. So again, null vector condition is satisfied. This and this, we'll see that m dot m will also give us 0. And same here with the alphas, they'll give us 0. And then the orthogonality conditions, L dotted with M will give us 0. And if we do N dotted with M, that will also give us 0 because there's two components here in the first two positions and then everything's 0. Whereas here there's only components in the last two positions, so it all cancels out. The normalizing condition, L dot n, when we do that, we'll end up with -1, which works. Or if we do it this way, we're going to end up with -1, so that works. And m dot m bar, if we do that, work that out, we'll also find that that comes to 1 as well. All right. Now, actually, when we do that, that's that one with that one, sorry. And we'll find that that comes to +1. All right. Right. Now, this approach to general relativity is known as the Newman Penrose Formalism, and it's particularly useful in solving problems involving the study of gravitational radiation. Now, it begins by finding a null tetrad at each point of space-time and then using this to find other quantities. In this video, we've just found the null tetrad. That's all we've done. The next step in dealing with this formalism is to start looking at spin coefficients and calculating various other quantities. But the very beginning of it is to find this null tetrad, which has been the focus of this video.